At approximately 10 o'clock in the morning on August 27, 1883, the island volcano of Krakatoa, situated in the Sunda Strait between the islands of Java and Sumatra in what was then the Dutch East Indies, produced an explosion of such extraordinary acoustic magnitude that it remains, more than a century later, generally regarded by acoustic scientists and volcanologists as the loudest sound event ever directly documented through scientific instrumentation in recorded human history. The sound of this explosion was clearly heard by human observers at a documented distance of approximately 3,000 miles from the volcano itself, on the island of Rodriguez near Mauritius in the Indian Ocean, where local residents, possessing no possible way of understanding what they were actually hearing, reported what they described as the sound of distant cannon fire or naval gunfire, a sound whose true origin would only become clear to these distant listeners considerably later. Once news of the catastrophic eruption had traveled back to them through the relatively nascent international telegraph communication networks that, in a historically significant coincidence, had only recently been established across much of the colonized world by 1883. The eruption's sheer destructive violence, considered independently of its remarkable acoustic properties, produced consequences of catastrophic and immediate severity for the populations living along the coastlines surrounding the Sunda Strait, with the volcanic explosion triggering a series of tsunamis that swept across the strait and along the adjacent coastlines of Java and Sumatra within minutes to hours following the eruption's most violent phase, ultimately killing more than 36,000 people according to the most widely cited historical estimates, the overwhelming majority of these deaths resulting directly from tsunami inundation rather than from any direct contact with volcanic material itself. Beyond its immediate and catastrophic local destruction, the Krakatoa eruption produced atmospheric effects of genuinely global reach and genuinely global duration, with volcanic ash and sulfate aerosols injected into the upper atmosphere subsequently circling the entire planet multiple times over the following weeks, producing strikingly vivid and widely documented atmospheric optical phenomena, including unusually intense red and orange sunset coloration observed and extensively documented by contemporary witnesses in locations as geographically distant from the eruption site as London, New York, and numerous other cities across Europe and North America, for a period extending well beyond a full year following the initial eruption itself. Tonight we reconstruct this catastrophic eruption in careful detail, tracing both its immediate and devastating local consequences and its remarkable and genuinely global atmospheric and acoustic effects, examining how the relatively new international telegraph network transformed this eruption into what many historians of science and communication consider the first natural disaster that populations across the entire globe learned about and followed in something approaching genuine real time. A historically significant development in the broader history of how human societies have experienced and processed catastrophic natural events occurring at great geographic distance from their own immediate communities. The island of Krakatoa itself, prior to its catastrophic 1883 eruption, was a relatively modest and relatively unremarkable volcanic island situated within the Sunda Strait, the body of water separating the much larger islands of Java and Sumatra within what was then the Dutch East Indies colonial territory, a strategically and commercially significant waterway connecting the Indian Ocean to the Java Sea and serving as an important shipping route for vessels traveling between Europe and the broader East Asian trading region. The volcanic island had experienced documented historical eruptions prior to 1883, including a notable period of eruptive activity recorded in the historical record of the 17th century, though the island had remained in a relatively dormant state for the considerable subsequent period leading up to the catastrophic events of 1883, with the volcano showing increasing and increasingly well-documented signs of renewed volcanic activity beginning in May 1883, several months before the climactic August eruption, including documented minor eruptions, increased seismic activity, and visible volcanic ash emission that attracted considerable contemporary scientific and journalistic attention from observers in the surrounding region, including from passing ship captains who documented and reported on the volcano's increasingly active state during this preliminary period. This several-month period of precursor volcanic activity, while ultimately proving catastrophically insufficient as a warning of the volcano's eventual climactic explosive eruption, nonetheless provided contemporary scientists and colonial administrators with several months of direct observational data regarding the volcano's developing activity. Data that subsequent volcanological researchers have found valuable in reconstructing the specific eruptive sequence and specific underlying geological processes that ultimately culminated in the catastrophic August 27 explosion, even as the scientific understanding of volcanic processes available in 1883 remained considerably too limited to allow contemporary observers to predict the specific timing or specific catastrophic severity of the eruption that would eventually occur. The specific geological setting of Krakatoa, situated along the same broader tectonic subduction zone system responsible for the volcanic activity throughout the Indonesian archipelago, including the considerably earlier and considerably more catastrophic 1815 Tambora eruption discussed in connection with a separate historical volcanic catastrophe, reflects the broader pattern of volcanic activity that characterizes this particular geological region as one of the most volcanically active areas on the entire planet, a consequence of the ongoing subduction of the Indo-Australian tectonic plate beneath the Eurasian plate that continues to generate volcanic activity throughout the Indonesian archipelago into the present day. The specific demographic and economic context of the Sunda Strait region in 1883, including its substantial coastal population engaged in fishing, agriculture, and maritime commerce connected to the strait's significant role in regional and international shipping, meant that the volcano's eventual catastrophic eruption would strike a densely populated and economically significant coastal region, rather than occurring in some more remote and less populated location, a geographic circumstance that contributed substantially to the eruption's catastrophic human toll once its climactic explosive phase and associated tsunamis finally occurred. The specific climactic eruption sequence that occurred on August 26 and 27, 1883, unfolded as an escalating series of increasingly violent explosive events, ultimately culminating in the morning of August 27 in what volcanologists studying the eruption have characterized as 4 particularly massive and particularly catastrophic explosions, the last and most violent of which, occurring at approximately 10:17 in the morning local time, produced the singularly loudest and most destructive event within this broader eruptive sequence. This final and most catastrophic explosion is generally understood by volcanologists studying the eruption to have resulted from the catastrophic collapse of a substantial portion of the volcanic island itself into the partially emptied magma chamber that had been progressively evacuated through the preceding hours of escalating eruptive activity, a process that generated an explosion of such extraordinary violence that it is estimated to have released energy equivalent to many thousands of times the energy released by the atomic bomb dropped on Hiroshima, producing an explosion whose specific acoustic signature was subsequently documented by barometric pressure recording instruments at meteorological stations distributed across the entire globe, instruments that recorded the passage of the eruption's atmospheric pressure wave as it propagated outward from the eruption site and, remarkably, continued to circle the entire planet multiple additional times over the following days, a phenomenon that provided contemporary scientists with their first opportunity to directly document and measure the global propagation of an atmospheric pressure wave generated by a single specific terrestrial event. The eruption's explosive violence destroyed approximately 2/3 of the original island of Krakatoa itself, with the volcanic structure that had previously risen above the strait's surface largely collapsing into the underlying caldera structure that the explosive evacuation of the volcano's magma chamber had created, leaving only a comparatively modest remnant of the original island structure remaining above sea level following the eruption's conclusion, a dramatic physical transformation of the local geography that subsequent volcanological surveys and subsequent direct observation confirmed in considerable detail. The specific volume of volcanic material ejected during this catastrophic eruptive sequence, estimated by volcanologists at approximately 20 cubic kilometers of rock, ash, and pumice, represents one of the largest documented volcanic ejecta volumes associated with any historically observed eruption, providing the underlying physical basis for both the eruption's catastrophic immediate local destructive effects and its remarkable and genuinely global atmospheric consequences, as this enormous volume of ejected material, including substantial quantities of fine ash and sulfur-bearing aerosol-forming compounds, was distributed both locally across the immediate eruption region and, for the finest and most readily atmospherically transported material, across the entire global atmosphere over the following weeks and months. The specific acoustic phenomenon that has made the Krakatoa eruption particularly famous and particularly scientifically significant within the broader history of recorded natural disaster centers on the extraordinary distance across which the eruption's sound was documented to have traveled and to have remained audible to human observers. A phenomenon that subsequent acoustic and atmospheric scientific analysis has helped to explain through careful examination of the specific atmospheric conditions and specific acoustic propagation mechanisms involved. The documented reports of the eruption's sound being clearly heard by human observers at the island of Rodriguez, located approximately 3,000 miles from Krakatoa across the Indian Ocean, represent one of the most extensively documented and most scientifically remarkable instances of long-distance sound propagation associated with any historically recorded terrestrial event. With local residents at this extraordinary distance reporting sounds they initially interpreted as distant naval gunfire or cannon fire, an interpretation that, while ultimately incorrect regarding the sound's actual source, reflects a reasonable contemporary attempt to explain a genuinely unusual and genuinely loud distant sound using the most plausible explanatory framework available to observers who possessed no reason whatsoever to suspect that a volcanic eruption occurring on the opposite side of the Indian Ocean could possibly produce a sound audible at such an extraordinary distance. The specific scientific explanation for this remarkable long-distance sound propagation, developed through subsequent acoustic and atmospheric physics research conducted across the decades following the eruption itself, centers on the eruption's generation of extremely low-frequency acoustic waves, including frequencies below the threshold of normal human hearing, sometimes described using the term infrasound. Frequencies that propagate through the atmosphere with considerably less energy loss over long distances compared to the higher frequency sound waves that characterize most everyday sound sources, allowing these specific low-frequency acoustic waves to travel considerably further while retaining sufficient energy to remain detectable, whether through direct human hearing at the lower end of this frequency range or through specialized acoustic instrumentation, at distances that would be entirely impossible for more typical higher-frequency sound sources to achieve. Contemporary barometric pressure recording instruments, maintained at meteorological observation stations across the globe as part of the routine weather monitoring infrastructure that had been established in numerous countries by the 1880s, documented the passage of distinct atmospheric pressure pulses corresponding to the Krakatoa eruption's most violent explosive phase, with these pressure pulses detected circling the entire planet multiple times over the course of several subsequent days, providing scientists with direct instrumental confirmation of the eruption's genuinely planetary-scale atmospheric acoustic impact, a finding that, when subsequently analyzed and published in the scientific literature, provided some of the earliest and most compelling direct scientific evidence demonstrating that a single terrestrial event could generate atmospheric disturbances capable of genuinely global propagation and genuinely global detection. The specific tsunamis generated by the Krakatoa eruption's most violent explosive phases represented the primary mechanism through which this volcanic catastrophe produced its overwhelming human death toll, with these waves striking the densely populated coastlines surrounding the Sunda Strait within a time frame of mere minutes to a small number of hours following the eruption's climactic explosions, leaving coastal populations with little to no practical opportunity for evacuation or other protective response. The specific mechanism generating these catastrophic tsunamis remains a subject of some continuing scientific discussion and continuing scientific research, with volcanologists and tsunami researchers examining several potential contributing mechanisms, including the displacement of seawater connected to the volcanic island's partial structural collapse into the underlying caldera, pyroclastic flows entering the surrounding sea with sufficient volume and velocity to generate significant water displacement, and the direct atmospheric pressure wave generated by the eruption's most violent explosions potentially contributing additional energy to the resulting wave systems, with the most likely current scientific understanding suggesting that some combination of these multiple potential mechanisms operating simultaneously or in close succession likely contributed to the eruption's overall catastrophic tsunami generation. Historical accounts and subsequent scientific reconstruction indicate that these tsunamis reached documented heights of more than 30 meters at certain coastal locations particularly exposed to the wave's direct path, with the waves sweeping considerable distances inland across the low-lying coastal plains characteristic of much of the Sunda Strait coastline, destroying entire coastal towns and villages and producing the overwhelming majority of the eruption's documented death toll of more than 36,000 people, a catastrophic human cost that dwarfed the comparatively limited direct mortality connected to volcanic ash, pyroclastic material, or other direct volcanic hazards associated with the eruption itself. The specific Dutch colonial administrative records maintained for this region during this historical period, while necessarily limited by the considerable practical challenges of conducting comprehensive mortality assessment across a region that had just experienced such catastrophic and widespread destruction, nonetheless provided historians and subsequent demographic researchers with a foundational documentary basis for the mortality estimates that continue to be cited in contemporary historical and scientific literature addressing this catastrophic eruption, even as some subsequent scholarly discussion has examined whether these original colonial-era mortality estimates may have somewhat undercounted the actual total mortality, particularly regarding mortality within more remote or less administratively documented coastal communities that may have experienced significant destruction without generating the kind of detailed contemporary administrative documentation that more accessible and more thoroughly documented communities received. The specific atmospheric and climatic consequences of the Krakatoa eruption, unfolding across the months and years following the initial catastrophic explosive events, represent another genuinely significant dimension of this eruption's broader historical and scientific importance, connecting this specific volcanic event to the broader scientific understanding of how major volcanic eruptions can influence global climate and global atmospheric conditions. The eruption injected substantial quantities of volcanic ash and sulfur dioxide gas into the upper atmosphere, with the sulfur dioxide subsequently converting into sulfate aerosol particles through atmospheric chemical processes broadly comparable to those discussed in connection with the considerably larger 1815 Tambora eruption, producing a stratospheric aerosol veil that circulated around the entire planet and that produced documented and extensively recorded optical effects, including unusually vivid and unusually prolonged red, orange, and purple sunset and sunrise coloration that was observed and extensively documented by contemporary witnesses across Europe, North America, and numerous other regions of the world for a period extending well beyond a full year following the initial 1883 eruption. These striking atmospheric optical phenomena attracted considerable contemporary scientific and artistic attention, with numerous contemporary newspapers, scientific journals, and individual observers documenting and attempting to explain these unusual atmospheric coloration effects, in some cases initially attributing the phenomena to entirely unrelated causes before the connection to the Krakatoa eruption's volcanic aerosol injection became more widely understood and more widely accepted. Within the contemporary scientific community, a process of scientific understanding development that proceeded considerably more rapidly than had been the case following the earlier 1815 Tambora eruption, reflecting the more advanced state of contemporary atmospheric and volcanic science available by the 1880s compared to the considerably more limited scientific understanding available in the early 19th century. The specific measurable global temperature effects connected to the Krakatoa eruption's stratospheric aerosol injection, while documented by contemporary and subsequent climatological analysis as producing a measurable and scientifically significant global cooling effect during the period immediately following the eruption, were generally considered by subsequent climatological researchers to be somewhat less severe and somewhat less prolonged compared to the considerably larger atmospheric and climatic effects connected to the earlier and considerably more massive 1815 Tambora eruption, a comparative difference that researchers have connected to Krakatoa's somewhat smaller total eruptive volume and somewhat smaller total atmospheric sulfur injection compared to the earlier and considerably larger Tambora event, even as both eruptions clearly demonstrated the same broader scientific principle regarding how major volcanic eruptions can produce measurable global climatic effects through stratospheric aerosol injection. The role that the relatively recently established International Telegraph Communication Network played in transmitting news of the Krakatoa eruption to audiences across the globe represents one of the more historically significant and most frequently discussed dimensions of this eruption's broader historical importance, connecting this specific volcanic catastrophe to the broader history of global communication technology development. By 1883, an extensive network of submarine telegraph cables had been established connecting Europe, the Americas, and much of the colonized world, including telegraph connections linking the Dutch East Indies to the broader global telegraph network, infrastructure that had been progressively developed across the preceding decades primarily to serve colonial administrative, commercial, and military communication needs, but that, in the specific case of the Krakatoa eruption, proved capable of transmitting news of this catastrophic natural disaster to audiences across the globe within a remarkably compressed time frame compared to the weeks or months that comparable news would have required to reach distant audiences in earlier historical periods, prior to the development of this telegraph communication infrastructure. Newspapers across Europe, North America, and numerous other regions of the world published detailed coverage of the eruption within days of its occurrence, drawing on telegraph dispatches transmitted from colonial administrative officials, ship captains, and other observers in the immediate vicinity of the eruption. Coverage that historians of media and communication have specifically examined as an important early example of how telegraph communication technology was beginning to transform the speed and the global reach of contemporary news reporting regarding major distant events, creating what several media historians have specifically characterized as one of the first instances of a natural disaster generating something approaching genuinely global, near real-time public awareness and public interest, a pattern of rapid global news transmission that would become considerably more developed and considerably more pronounced in subsequent decades as telegraph, and subsequently telephone and radio communication technology continued to develop. This historically significant connection between the Krakatoa eruption and the broader development of global telegraph communication technology illustrates a genuinely important pattern in the broader history of how human societies have experienced and processed news of distant catastrophic events, with the eruption representing a kind of historical inflection point at which the technological capacity for rapid global communication had developed sufficiently to allow populations across the globe to learn about and follow a major distant natural disaster within a time frame of days rather than the weeks or months that had characterized the transmission of comparable news in earlier historical periods, including, notably, the considerably slower transmission of news regarding the earlier 1815 Tambora eruption, whose full global significance and full global atmospheric consequences would not become widely understood by contemporary populations across the globe until considerably more time had elapsed compared to the relatively rapid contemporary global awareness that the Krakatoa eruption achieved through this developing telegraph communication infrastructure. The scientific response to the Krakatoa eruption, including the systematic international scientific effort to document and analyze the eruption's various physical, atmospheric, and oceanic consequences, represents an important early example of organized international scientific collaboration addressing a major natural disaster, reflecting the increasingly internationally coordinated character of late 19th century scientific research more broadly. The Royal Society of London established a dedicated scientific committee specifically tasked with systematically collecting, analyzing, and publishing observational data regarding the Krakatoa eruption's various global atmospheric and oceanic effects, drawing on observational reports and data submitted by scientists, ship captains, colonial administrators, and other observers from across the globe. Work that culminated in the publication of a comprehensive scientific report addressing the eruption's documented global consequences, a report that represented one of the more ambitious and most comprehensive international scientific data collection and analysis efforts undertaken in connection with any single natural disaster up to that point in the broader history of scientific research. This Royal Society investigation specifically documented and analyzed the global atmospheric pressure wave phenomena discussed previously, drawing on barometric pressure recording data submitted from meteorological observation stations distributed across the globe. Work that provided some of the earliest scientifically rigorous documentation and analysis of genuinely global-scale atmospheric pressure wave propagation connected to a single specific terrestrial event, contributing significantly to the developing scientific understanding of large-scale atmospheric physics and atmospheric wave propagation that would continue to develop across subsequent decades of meteorological and atmospheric scientific research. The specific scientific documentation and analysis of the eruption's striking atmospheric optical effects, including the widely observed and widely documented unusual sunset and sunrise coloration phenomena, similarly drew on observational reports submitted by scientists and other interested observers across the globe, contributing to the developing contemporary scientific understanding regarding how volcanic eruptions could influence atmospheric optical properties through the injection of fine particulate and aerosol material into the upper atmosphere, understanding that would continue to develop and that would eventually contribute to the considerably more sophisticated scientific understanding of volcanic atmospheric and climatic effects that subsequent 20th and 21st century researchers, studying both the Krakatoa eruption itself and other major volcanic events including Tambora and the more recent 1991 Pinatubo eruption, would eventually develop using progressively more sophisticated scientific instrumentation and progressively more sophisticated atmospheric and climatic modeling techniques. This relatively early example of internationally coordinated scientific investigation addressing a major natural disaster's global consequences illustrates how the Krakatoa eruption, beyond its catastrophic immediate human toll and its remarkable acoustic and atmospheric properties, also occupies a historically significant position within the broader development of international scientific collaboration and international scientific data collection methodology, contributing to broader patterns of scientific institutional development that would continue to evolve across the subsequent decades of 20th century scientific research addressing major natural disasters and major global environmental phenomena. The subsequent volcanic history of the Krakatoa region, including the eventual emergence and ongoing development of a new volcanic structure within the caldera created by the catastrophic 1883 eruption, represents an important and ongoing dimension of this region's continuing geological and volcanological significance. Beginning in 1927, volcanic activity was documented re-emerging within the submerged caldera that the 1883 eruption had created, ultimately producing a new volcanic island that emerged above sea level and that received the name Anak Krakatau, meaning child of Krakatoa in Indonesian, reflecting the new volcanic structure's geological relationship to its catastrophically destroyed predecessor, with this new volcanic island subsequently experiencing numerous additional eruptive episodes across the following decades, gradually building additional volcanic material and gradually increasing in size through this ongoing pattern of periodic volcanic activity. This ongoing volcanic activity at Anak Krakatau has continued to attract considerable scientific attention and considerable scientific monitoring, given the region's demonstrated historical capacity for catastrophic explosive volcanic activity, with volcanologists maintaining ongoing observational and instrumental monitoring of this developing volcanic structure specifically intended to provide early warning of any future eruptive activity that might pose renewed catastrophic risk to the considerable coastal population that continues to inhabit the surrounding Sunda Strait region in the contemporary period. In December 2018, a substantial portion of the Anak Krakatoa volcanic structure experienced a catastrophic partial collapse connected to renewed volcanic eruptive activity, generating a tsunami that struck nearby coastlines and that killed more than 400 people, a considerably smaller though still genuinely catastrophic event compared to the original 1883 eruption, but one that nonetheless served as a sobering and historically resonant demonstration that the broader geological hazards historically associated with this specific volcanic region, including the specific combination of explosive volcanic activity and associated tsunami generation that characterized the original 1883 catastrophe, continue to represent a genuine and ongoing risk to the considerable contemporary population inhabiting the surrounding coastal areas. This continuing pattern of volcanic activity and continuing demonstrated tsunami risk at the Krakatoa site illustrates how this specific geological location, despite the more than a century that has elapsed since its original catastrophic 1883 eruption, continues to represent an active and ongoing focus of volcanological scientific research and ongoing natural disaster risk management concern, connecting the historical catastrophe this documentary has examined directly to continuing contemporary scientific and policy efforts focused on monitoring and, to whatever extent scientifically possible, mitigating the risk that this geologically active region continues to pose to its surrounding contemporary population. The comparison between the Krakatoa eruption and other major historically documented volcanic eruptions, including both the earlier 1815 Tambora eruption and the more recent 1991 eruption of Mount Pinatubo in the Philippines, provides volcanologists and historians with valuable comparative perspective regarding the range of physical characteristics and the range of consequences that major explosive volcanic eruptions can produce. While the 1815 Tambora eruption is generally considered by volcanologists to have involved a somewhat larger total eruptive volume and to have produced somewhat more severe and somewhat more prolonged global atmospheric and climatic consequences compared to Krakatoa, the Krakatoa eruption's specific combination of catastrophic tsunami generation and remarkable acoustic propagation properties has made it, in certain specific respects, an even more scientifically and historically significant event for researchers specifically interested in studying these particular categories of volcanic eruption consequence, with Krakatoa's documented acoustic and tsunami effects providing researchers with considerably more detailed and considerably more scientifically rigorous documentation compared to the considerably less thoroughly documented comparable effects connected to the earlier Tambora eruption, reflecting the more advanced state of contemporary scientific instrumentation and contemporary scientific observational methodology available by the 1880s compared to the early 19th century period in which the Tambora eruption occurred. The considerably more recent 1991 Pinatubo eruption, occurring during a period of considerably more advanced contemporary scientific instrumentation and contemporary scientific monitoring capability compared to either of these two historically earlier eruptions, has provided volcanologists with the most scientifically detailed and most comprehensively instrumented direct observational data regarding the specific atmospheric and climatic consequences that a major explosive volcanic eruption can produce, data that researchers have subsequently used to refine and to test the scientific models and scientific understanding initially developed through historical research addressing both the Tambora and Krakatoa eruptions, illustrating how the scientific understanding of major volcanic eruption consequences has continued to develop and to be refined through the cumulative comparative study of multiple historically documented eruption events, each occurring during a period of somewhat different available scientific instrumentation and somewhat different available scientific observational methodology. This broader comparative volcanological research, examining the Krakatoa eruption alongside these other major historically documented eruptions, has contributed significantly to contemporary scientific understanding regarding the general relationship between specific volcanic eruption characteristics, including total eruptive volume, specific eruption location and geological setting, and specific atmospheric sulfur and aerosol injection quantity, and the resulting severity and resulting global reach of the eruption's various atmospheric, climatic, and, in cases including Krakatoa specifically, oceanic tsunami consequences, contributing to the kind of refined scientific risk assessment models that contemporary volcanologists and natural disaster risk management researchers continue to develop and to apply in their ongoing efforts to assess and to communicate the potential risks that future major volcanic eruptions, wherever and whenever they might eventually occur, could pose to contemporary global populations. The individual human experiences and individual human stories connected to the Krakatoa eruption, documented through surviving contemporary accounts, colonial administrative records, and subsequent historical research, provide an essential human dimension to this broader scientific and historical narrative that complements the more technical volcanological and acoustic scientific evidence discussed throughout this documentary. Ship captains navigating the Sunda Strait and surrounding waters during the eruption's most violent phases documented their direct first-hand experiences in considerable and often genuinely harrowing detail, with several surviving ship logs and subsequent published accounts describing experiences including ash falling so heavily on ship decks that crews were required to continuously clear it to prevent excessive weight accumulation, complete darkness descending during daylight hours as the eruption's ash cloud blocked sunlight, and the genuinely terrifying experience of navigating through and around the enormous tsunami waves that the eruption's most violent explosive phases generated. Accounts that provide historians with some of the most detailed and most vivid surviving first-hand documentation of the eruption's immediate physical effects as experienced by individuals in relatively close proximity to the eruption site itself. The considerable loss of life among the coastal populations of Java and Sumatra, documented through Dutch colonial administrative records compiled in the eruption's immediate aftermath, represented the human reality underlying the broader mortality statistics that this documentary has discussed. With these colonial records documenting the complete destruction of numerous coastal towns and villages and the deaths of entire families and entire communities within the brief time frame of the tsunami wave's arrival, a catastrophic human cost that, while necessarily documented through the inevitably limited and inevitably imperfect lens of contemporary colonial administrative record-keeping, nonetheless provides historians with essential evidence regarding the genuinely catastrophic human dimension of this volcanic disaster. Surviving accounts from individuals who experienced the eruption's effects at considerable geographic distance from the eruption site itself, including the previously discussed accounts from observers on Rodriguez Island who heard the eruption's sound without understanding its source, and including numerous additional contemporary accounts documenting individual reactions to the eruption's widely observed atmospheric optical effects in Europe and North America, provide historians with valuable evidence regarding how this single catastrophic volcanic event was experienced and processed by individuals across an extraordinarily wide range of geographic distance and an extraordinarily wide range of personal circumstance, from the immediate and catastrophic mortal danger experienced by coastal populations in the immediate vicinity of the eruption to the considerably more distant and considerably more aesthetically and scientifically curious experience of observers in Europe and North America who encountered this same catastrophic event primarily through its remarkable and widely discussed atmospheric optical aftereffects. These varied individual human accounts, ranging from the genuinely terrifying direct experience of ship captains and coastal residents in immediate proximity to the eruption to the considerably more removed but still genuinely significant experience of distant observers documenting unusual sunsets and unusual distant sounds, collectively illustrate the genuinely wide-ranging and genuinely global human experience that this single catastrophic volcanic eruption produced, connecting the specific and catastrophic local human tragedy that this eruption produced to the broader and genuinely global pattern of human observation, human scientific curiosity, and human historical memory that this remarkable natural disaster subsequently generated across populations and across geographic regions far removed from the immediate site of the eruption itself. The contemporary scientific understanding regarding the precise acoustic and atmospheric physics underlying the Krakatoa eruption's remarkable long-distance sound propagation has continued to develop through subsequent decades of acoustic and atmospheric physics research, building upon the foundational 19th-century observational data and 19th-century scientific analysis discussed previously. Researchers studying infrasound, the category of extremely low-frequency acoustic waves below the threshold of normal human auditory perception that played a central role in the Krakatoa eruption's remarkable long-distance acoustic propagation, have continued to develop increasingly sophisticated scientific understanding regarding exactly how these specific low-frequency acoustic waves propagate through the atmosphere across very long distances, research that has been considerably advanced. Through the development of dedicated infrasound monitoring instrumentation and dedicated infrasound monitoring networks established during the 20th and 21st centuries, including instrumentation networks originally developed primarily for nuclear weapons test monitoring purposes but subsequently applied more broadly to the scientific study of natural infrasound sources, including volcanic eruptions, meteor impacts, and other large-scale natural and artificial sources of low-frequency atmospheric acoustic disturbance. This subsequent scientific research has confirmed and has considerably refined the basic 19th-century scientific understanding that the Krakatoa eruption's remarkable long-distance audibility depended specifically on the eruption's generation of acoustic energy concentrated within these particular low-frequency infrasound frequency ranges. Frequencies that experience considerably reduced atmospheric absorption and considerably reduced atmospheric scattering compared to higher frequency sound waves, allowing this specific category of acoustic energy to propagate across considerably greater distances while retaining sufficient energy to remain detectable, whether through direct human auditory perception at the upper boundary of the infrasound frequency range or through specialized acoustic instrumentation specifically designed to detect lower frequency acoustic signals beyond the range of normal human hearing. Contemporary acoustic modeling research, applying considerably more sophisticated computational atmospheric acoustic propagation modeling techniques to the historical Krakatoa eruption data compared to what was scientifically feasible during the 19th century period when the eruption itself occurred, has worked to develop increasingly precise quantitative reconstructions of the eruption's specific acoustic energy output and specific acoustic propagation characteristics, research that has generally confirmed the broad historical understanding of the eruption as representing an exceptionally powerful acoustic event, while also providing considerably more precise and considerably more scientifically rigorous quantitative characterization of exactly how acoustically powerful this remarkable eruption actually was, in terms that allow direct comparison to other documented acoustic phenomena using the kind of standardized acoustic measurement units and standardized acoustic measurement methodology that simply did not exist during the historical period when the original eruption itself occurred. This continuing scientific research into the specific acoustic physics underlying the Krakatoa eruption's remarkable long-distance audibility illustrates how this historical natural disaster has continued to serve as a valuable scientific case study and valuable scientific reference point for researchers working in the considerably more specialized and considerably more technically developed contemporary field of atmospheric infrasound research, connecting this historical 19th century volcanic catastrophe to ongoing and genuinely active contemporary scientific research addressing the broader physics of long-distance atmospheric acoustic propagation. The specific role that the Krakatoa eruption played within the broader artistic and cultural production of the late 19th century, particularly in connection with its widely observed and widely documented atmospheric optical effects, represents another genuinely significant dimension of this eruption's broader historical and cultural legacy. The unusually vivid and unusually prolonged red and orange sunset coloration that the eruption's stratospheric aerosol veil produced across Europe, North America, and numerous other regions of the world attracted considerable contemporary artistic attention, with several art historians having subsequently examined and analyzed the painted work of various contemporary landscape artists working during this period for documented evidence of these unusual atmospheric coloration effects influencing their artistic representation of sky and sunset coloration during the months and years immediately following the 1883 eruption. Research broadly comparable to the similar art historical research previously discussed in connection with the considerably earlier Tambora eruptions documented influence on the work of contemporary painters including J.M.W. Turner. The painter Edvard Munch's famous and widely recognized work The Scream, completed in the early 1890s, has been the subject of specific art historical speculation regarding a possible connection to the artist's own documented personal recollection of having witnessed unusually vivid and unusually striking red sky coloration during this general historical period, with Munch's own subsequent written accounts describing his personal recollection of witnessing a sky that turned blood red during a walk he took at some point during this general period, a description that several researchers studying this question have connected, with appropriate scholarly caution regarding the inherent difficulty of definitively establishing such a specific historical and biographical connection, to the documented and widely observed Krakatoa-related atmospheric optical phenomena that were being observed and discussed across Europe during this same general historical period. Contemporary newspaper coverage and contemporary popular scientific publications addressing the eruption's widely observed atmospheric optical effects generated considerable public interest and considerable public discussion across Europe and North America during the months and years following the initial eruption, with numerous contemporary publications specifically devoted to documenting, illustrating, and attempting to scientifically explain these unusual and widely observed atmospheric phenomena, contributing to a broader pattern of contemporary public engagement with and public fascination regarding this distant volcanic catastrophe's remarkable and visually striking atmospheric aftereffects, even among populations who, unlike the immediately affected coastal populations of Java and Sumatra, experienced this catastrophic natural disaster's consequences in the considerably more removed and considerably more aesthetically oriented form of unusually beautiful, if scientifically puzzling, sunset and sunrise sky coloration. This documented pattern of contemporary artistic and cultural engagement with the eruption's atmospheric optical aftereffects, extending considerably beyond the more narrowly scientific and more narrowly journalistic documentation discussed previously, illustrates how this catastrophic volcanic eruption's genuinely global atmospheric consequences penetrated into the broader cultural and artistic consciousness of populations across the globe during this historical period, providing a genuinely significant example of how a major natural disaster occurring at one specific geographic location can generate consequences, including artistic and cultural consequences, extending to populations and to cultural production occurring at very considerable geographic remove from the disaster's actual immediate physical impact zone. The contemporary scientific and policy significance that the Krakatoa eruption continues to hold for ongoing volcanic hazard assessment and ongoing tsunami early warning system development represents an important and genuinely practical dimension of this historical eruption's continuing relevance to contemporary natural disaster risk management. Volcanologists and tsunami researchers studying the specific mechanisms by which the Krakatoa eruption generated its catastrophic tsunami waves have used this historical case study to inform the development of contemporary volcanic tsunami hazard assessment models, work that has become particularly significant in the aftermath of the 2018 Anak Krakatoa collapse and associated tsunami discussed previously, an event that researchers have specifically studied as a smaller scale but mechanistically comparable demonstration of the same broader category of volcanic tsunami generation mechanism that produced the considerably more catastrophic 1883 tsunami waves, providing researchers with valuable additional direct observational data regarding exactly how volcanic structural collapse events can generate tsunami waves. Data that has subsequently been incorporated into refined scientific models addressing this specific category of natural hazard. The considerable historical mortality connected to the Krakatoa eruption's tsunami waves, occurring within a population that possessed essentially no advance warning of the impending tsunami threat, given the complete absence of any tsunami early warning system or any comparable natural disaster early warning infrastructure during this historical period, has contributed to broader contemporary policy discussions regarding the importance of developing and maintaining effective tsunami early warning systems specifically capable of detecting volcanic structural collapse events and other volcanic tsunami generation mechanisms, a category of tsunami threat that contemporary tsunami early warning systems, which have historically focused considerable attention on the more statistically common category of tsunamis generated by major submarine earthquakes, have in some cases been criticized by researchers as providing somewhat less comprehensive or somewhat less immediately responsive detection and warning capability compared to the warning capability these systems generally provide for earthquake-generated tsunami threats. The specific Indonesian government's subsequent development and subsequent ongoing refinement of volcanic monitoring and tsunami early warning infrastructure specifically covering the Krakatoa region, including infrastructure developed and refined both before and, with particular subsequent urgency, following the 2018 Anak Krakatoa collapse event, illustrates the genuinely practical and genuinely consequential contemporary policy response that this region's demonstrated historical and ongoing volcanic and tsunami hazard has generated. Connecting the historical catastrophe of 1883 directly to ongoing contemporary natural disaster risk management policy and ongoing contemporary natural disaster early warning infrastructure development specifically focused on protecting the considerable contemporary population that continues to inhabit the historically hazardous coastal regions surrounding this geologically active volcanic site. This ongoing and genuinely practical contemporary scientific and policy engagement with the continuing volcanic and tsunami hazard that the Krakatoa region represents illustrates how the historical study of this 19th-century volcanic catastrophe continues to inform genuinely consequential contemporary natural disaster risk management policy and infrastructure development. Connecting the historical events this documentary has examined directly to ongoing contemporary efforts specifically focused on protecting present-day populations from the continuing risk that this demonstrably active and demonstrably hazardous volcanic region continues to represent. The question of how the Krakatoa eruption's remarkable acoustic properties compare to other documented loud sound events, both natural and artificial, in the broader history of acoustic science and acoustic measurement, provides an interesting and genuinely informative point of comparison for understanding exactly how extraordinary this particular eruption's acoustic output actually was. Contemporary acoustic scientists, applying modern acoustic measurement standards and modern acoustic measurement units to the historical barometric pressure data documenting the Krakatoa eruption's atmospheric pressure wave, have estimated that the eruption sound, measured at a standardized reference distance, would have registered at an acoustic intensity level very considerably exceeding the threshold at which sustained exposure produces permanent human hearing damage, with some acoustic researchers specifically estimating that observers located within approximately 40 miles of the eruption site would likely have experienced ruptured eardrums purely as a direct consequence of the sound pressure level the eruption generated at this comparatively close distance, an estimate that, while necessarily involving some degree of scientific extrapolation, given the inherent limitations of reconstructing precise acoustic measurements from 19th-century barometric pressure recording. Instrumentation, nonetheless, provides a genuinely striking illustration of the eruption's extraordinary acoustic intensity. When compared to other documented extremely loud sound events that subsequent acoustic science has been able to measure using considerably more direct and considerably more contemporary acoustic measurement instrumentation, including major artificial explosions such as nuclear weapons tests and major rocket launches, the Krakatoa eruption continues to be generally regarded by acoustic scientists as representing the single loudest sound event ever documented through any form of scientific instrumentation, whether contemporary 19th-century barometric pressure recording or considerably more sophisticated subsequent acoustic measurement technology. a distinction that reflects both the eruption's genuinely extraordinary underlying physical energy release and the historically fortunate circumstance that this particular eruption occurred during a period when at least some forms of relevant scientific instrumentation, specifically the barometric pressure recording stations, maintained as part of contemporary meteorological monitoring infrastructure, happened to be available and happened to be capable of documenting the eruption's remarkable atmospheric pressure wave effects. This specific acoustic comparison and this specific acoustic measurement reconstruction work, while necessarily involving some degree of careful scientific extrapolation given the inherent limitations of applying contemporary acoustic measurement standards to historical 19th century instrumental data, nonetheless provides researchers and the broader public with a genuinely useful and genuinely informative quantitative framework for understanding exactly how extraordinary the Krakatoa eruption's documented acoustic properties actually were, helping to explain, in scientifically grounded quantitative terms, exactly why this particular volcanic eruption has continued to be specifically and repeatedly cited across more than a century of subsequent scientific and popular discussion, as representing the loudest sound event ever directly documented through scientific instrumentation in recorded human history. The broader pattern of how human societies have historically processed and historically commemorated the Krakatoa eruption within their collective historical memory and their collective cultural representation provides an interesting point of comparison to the broader patterns of historical memory formation discussed in connection with other major historical catastrophes this documentary series has previously examined. Unlike the considerably more limited and considerably more constrained popular historical memory connected to the earlier 1815 Tambora eruption, discussed previously in connection with that eruption's relative historical obscurity compared to its genuinely catastrophic global consequences, the Krakatoa eruption has maintained a considerably more prominent and considerably more sustained position within popular historical and scientific consciousness across the more than a century that has elapsed since its original occurrence, a difference that historians and historians of science have connected to several specific factors, including the considerably more advanced contemporary telegraph communication infrastructure that allowed news of the Krakatoa eruption to reach global audiences considerably more rapidly and considerably more extensively compared to the considerably slower and considerably more limited contemporary news transmission available during the earlier Tambora eruption period, and the considerably more advanced contemporary scientific instrumentation and contemporary scientific institutional infrastructure, including the Royal Society's dedicated investigative committee discussed previously, that allowed the Krakatoa eruption's scientific significance to be more systematically documented, more systematically analyzed, and more systematically publicized within the contemporary and subsequent scientific literature compared to the considerably more limited contemporary scientific documentation and contemporary scientific analysis that the earlier Tambora eruption initially received. The eruption's specific and genuinely remarkable acoustic properties, including the historically striking and historically memorable detail regarding the eruption's sound being clearly heard at the extraordinary documented distance of approximately 3,000 miles. Have provided this particular historical catastrophe with a specific and genuinely memorable narrative detail that has continued to feature prominently in popular historical and scientific discussion of the eruption across the subsequent decades, illustrating how specific, vivid, and genuinely remarkable individual details connected to a major historical catastrophe can contribute substantially to that catastrophe's subsequent prominence within popular historical memory and popular cultural representation, a pattern that connects to the broader historiographical discussion addressed in connection with several other historical catastrophes this documentary series has examined, regarding how specific narrative and representational factors, beyond simply the raw statistical magnitude of a given historical catastrophe's human or material consequences, can significantly influence that catastrophe's subsequent prominence within broader popular historical consciousness and broader popular cultural memory. This relatively more prominent and relatively more sustained popular historical memory connected to the Krakatoa eruption particularly when considered in comparative context alongside the considerably more limited popular historical memory connected to the earlier and, in certain respects, considerably more catastrophic Tambora eruption, illustrates the genuinely complex and genuinely multifaceted set of historical, technological, and narrative factors that collectively shape which major historical catastrophes receive sustained prominent attention within subsequent popular historical memory and which catastrophes, despite their own genuine and often very considerable historical significance, receive comparatively more limited subsequent popular historical attention and subsequent popular cultural representation. The subsequent scientific reassessment and subsequent scientific refinement of the original 19th century mortality estimates connected to the Krakatoa eruption represents an important dimension of how historical scientific understanding regarding this catastrophic event has continued to develop and to be refined across the more than a century of subsequent historical and scientific research addressing this disaster. The originally cited mortality estimate of approximately 36,000 deaths, derived primarily from contemporary Dutch colonial administrative records compiled in the eruption's immediate aftermath, has remained the most widely cited and most frequently referenced mortality figure within both popular and much of the academic literature addressing this eruption across the subsequent decades, even as some subsequent historical and demographic researchers have specifically examined whether this original colonial-era estimate may have somewhat undercounted the eruption's true total mortality, particularly regarding mortality occurring within more remote coastal communities that may have experienced significant tsunami destruction without generating the kind of detailed contemporary administrative documentation that more accessible and more thoroughly administratively documented communities received during the colonial mortality assessment process conducted in the eruption's immediate aftermath. This kind of careful subsequent historical and demographic reassessment of original contemporary mortality estimates connects to a broader and more general pattern that this documentary series has previously examined in connection with several other major historical catastrophes, including notably the similarly evolving and similarly upward-trending scholarly mortality estimates connected to the considerably earlier 1918 influenza pandemic, illustrating a more general historiographical pattern, in which original contemporary mortality estimates for major historical catastrophes, particularly catastrophes affecting populations within colonial territories or other populations subject to less comprehensive contemporary administrative documentation, have frequently required subsequent upward revision as subsequent generations of historians and demographic researchers have developed more sophisticated and more methodologically careful approaches to estimating mortality within populations that lacked comprehensive contemporary administrative record-keeping infrastructure. This ongoing scholarly reassessment of the Krakatoa eruption's precise mortality toll, while not yet having produced any single definitively established revised mortality figure capable of fully superseding the originally cited and still most commonly referenced figure of approximately 36,000 deaths, nonetheless illustrates the genuinely ongoing and genuinely active character of contemporary historical research addressing even well-established and well-documented historical catastrophes, with researchers continuing to apply increasingly sophisticated historical demographic research methodology to refine and to improve scholarly confidence regarding even those specific quantitative dimensions of historical catastrophes that might, to a casual contemporary observer, appear to represent settled and uncontested historical facts requiring no further scholarly investigation or scholarly refinement. The contemporary volcanic monitoring infrastructure currently maintained at the Krakatoa site, including the ongoing scientific surveillance specifically focused on Anak Krakatau's continuing volcanic activity, represents a genuinely significant practical legacy connecting this historical 1883 catastrophe to ongoing contemporary natural disaster risk management efforts. Indonesian volcanological authorities, working in coordination with international volcanological research institutions and international natural disaster risk management organizations, maintain ongoing seismic monitoring, ongoing gas emission monitoring, and ongoing visual and satellite-based monitoring of Anak Krakatoa's continuing volcanic activity. Monitoring infrastructure specifically designed to provide as much advance warning as scientifically possible regarding any future eruptive activity or any future structural instability that might pose renewed catastrophic risk to the considerable coastal population that continues to inhabit the surrounding Sunda Strait region in the contemporary period. The specific scientific and policy lessons that researchers and policymakers have drawn from the catastrophic 2018 Anak Krakatoa collapse and associated tsunami, discussed previously, have informed subsequent refinements to this ongoing monitoring infrastructure, including increased scientific attention to the specific category of volcanic structural collapse hazard that this particular event so dramatically illustrated, a category of volcanic hazard that, as discussed previously, has historically received somewhat less comprehensive monitoring and somewhat less comprehensive early warning system development compared to the more statistically common category of earthquake-generated tsunami hazards that most contemporary tsunami early warning systems were originally primarily designed to detect and to provide warning regarding. This ongoing and genuinely active contemporary scientific monitoring effort, while representing a considerably more scientifically sophisticated and considerably more technologically advanced approach to volcanic hazard assessment compared to the essentially complete absence of any comparable monitoring or warning infrastructure available during the original catastrophic 1883 eruption, nonetheless continues to confront genuine and significant scientific and practical challenges in attempting to provide fully reliable advance warning regarding future volcanic eruptive activity and future volcanic structural collapse events, challenges that reflect the genuinely complex and genuinely difficult underlying scientific challenge of precisely predicting the specific timing and specific severity of future volcanic eruptive activity, even when, as in the specific case of Anak Krakatoa, scientists maintain comprehensive and sophisticated ongoing monitoring of a volcanic structure whose historical and ongoing capacity for catastrophic eruptive activity has been so dramatically and so repeatedly demonstrated. The specific broader question of how contemporary global infrastructure and contemporary global communication networks might respond to a future volcanic eruption displaying acoustic and atmospheric characteristics genuinely comparable to the historical 1883 Krakatoa eruption represents an interesting and genuinely informative point of contemporary scientific and policy consideration. Contemporary global telecommunications infrastructure, including satellite communication networks, Internet-based communication systems, and considerably more extensive and considerably more rapid contemporary news media networks compared to the relatively nascent 19th-century telegraph infrastructure that originally transmitted news of the Krakatoa eruption, would almost certainly allow considerably more rapid and considerably more comprehensive global public awareness regarding a comparable future eruption event compared to the awareness that 19th-century telegraph infrastructure was capable of providing, illustrating the considerable subsequent development that global communication infrastructure has undergone across the more than a century since the original 1883 eruption occurred. Contemporary volcanological monitoring infrastructure, including the kind of dedicated seismic and gas emission monitoring networks discussed previously in connection with ongoing Anak Krakatoa surveillance, alongside considerably more sophisticated contemporary satellite-based volcanic monitoring capability that did not exist during the 19th century period, would likely provide considerably more advance warning regarding a developing eruption's increasing activity compared to the considerably more limited direct observational monitoring available during the original 1883 eruption's preliminary several-month period of precursor volcanic activity. Though contemporary volcanologists generally maintain appropriate scientific caution regarding the genuine and continuing limitations that exist in precisely predicting the specific timing and specific catastrophic severity of major explosive volcanic eruptions, even when comprehensive contemporary monitoring infrastructure is actively documenting a volcano's developing precursor activity. Contemporary tsunami early warning systems, while representing a considerably more developed and considerably more sophisticated category of natural disaster early warning infrastructure compared to the complete absence of any comparable warning infrastructure during the 1883 eruption, would likely provide at least some additional advance warning time to coastal populations facing a comparable future volcanic tsunami threat, though, as discussed previously, contemporary tsunami early warning systems have historically demonstrated somewhat less comprehensive detection and warning capability specifically regarding the category of volcanic structural collapse-generated tsunami threat that the original 1883 Krakatoa eruption and the more recent 2018 Anak Krakatoa collapse both specifically demonstrated, suggesting that, despite the very considerable scientific and technological progress that has occurred across the more than a century since the original eruption, coastal populations facing a genuinely comparable future volcanic tsunami threat might still face meaningfully limited advance warning time compared to the warning time that contemporary tsunami early warning systems are generally capable of providing for the more statistically common category of earthquake-generated tsunami threats. This careful contemporary scientific and policy consideration of how present-day infrastructure and present-day natural disaster risk management capability might respond to a future eruption genuinely comparable to the historical 1883 Krakatoa catastrophe illustrates both the very considerable scientific and technological progress that has occurred across the intervening century and the continuing and genuinely significant limitations that contemporary natural disaster risk management infrastructure continues to face when confronting the specific category of catastrophic volcanic hazard that this historical eruption so dramatically and so memorably demonstrated. The question of how the Krakatoa eruption connects to the broader scientific understanding of the Indonesian archipelago's continuing status as one of the most volcanically and seismically active regions on the entire planet provides important broader geological and geographic context for understanding this specific eruption's place within the broader pattern of regional volcanic and seismic hazard. The Indonesian archipelago, situated along the convergent boundary between multiple major tectonic plates, hosts more historically active volcanoes than any other country in the world, a geological circumstance that has produced numerous major historically documented volcanic eruptions beyond Krakatoa specifically, including the considerably earlier and considerably larger 1815 Tambora eruption discussed previously, along with numerous other significant historical eruptions occurring at various other Indonesian volcanic sites across the subsequent decades and centuries, reflecting the genuinely continuous and genuinely ongoing pattern of volcanic activity that characterizes this particular geological region as a consequence of its specific tectonic setting. This broader pattern of regional volcanic activity has motivated the development of considerably more comprehensive and considerably more systematic contemporary volcanic monitoring infrastructure across the Indonesian archipelago more generally, extending well beyond the specific dedicated monitoring infrastructure focused on Anak Krakatoa discussed previously, with Indonesian volcanological authorities maintaining ongoing monitoring of numerous additional historically active volcanic sites. Distributed across the archipelago, infrastructure development that reflects the considerable and ongoing contemporary scientific and policy recognition regarding the genuine and continuing volcanic hazard that this entire geological region represents for its considerable contemporary population. The specific scientific and historical connections between Krakatoa and these other major Indonesian volcanic sites, including the direct geological connection through the shared underlying tectonic subduction zone system responsible for volcanic activity throughout the entire region, illustrate how this specific 1883 eruption, while genuinely remarkable and genuinely historically significant in its own specific right, also represents one particularly well-documented example within a considerably broader and considerably more extensive pattern of major volcanic activity that has characterized, and that continues to characterize, this specific and geologically distinctive region of the world across a time frame extending considerably beyond the specific historical period that this documentary has primarily focused upon. This broader geological and geographic context, connecting Krakatoa to the considerably wider pattern of Indonesian volcanic activity more generally, illustrates how this specific historical eruption, despite its own genuine scientific and historical significance, represents one specific and particularly well-documented instance within a considerably broader and considerably more ongoing pattern of regional volcanic hazard that continues to shape contemporary scientific research priorities, contemporary natural disaster risk management policy, and contemporary public awareness regarding the genuine and continuing volcanic risks that this geologically distinctive and geologically active region of the world continues to represent for its considerable contemporary population. The scientific legacy that the Krakatoa eruption has left for the broader development of volcanology, acoustic science, and atmospheric science as recognized academic and scientific disciplines represents a genuinely significant dimension of this eruption's broader contribution to subsequent scientific development, extending considerably beyond the more immediate historical and human dimensions of this catastrophic event that this documentary has primarily examined throughout most of its preceding discussion. The specific scientific data and specific scientific documentation that the Krakatoa eruption generated, including the Royal Society's comprehensive scientific investigation discussed previously, provided subsequent generations of volcanologists, acoustic scientists, and atmospheric scientists with an unusually well-documented historical case study that has continued to inform and to ground subsequent theoretical and empirical scientific research across these multiple related scientific disciplines, illustrating how a single historical natural disaster, when sufficiently well documented through contemporary scientific investigation, can continue to provide genuinely valuable scientific data and genuinely valuable scientific case study material for subsequent generations of researchers working many decades after the original disaster event itself occurred. The specific development of infrasound monitoring as a recognized and scientifically significant subdiscipline within the broader field of atmospheric acoustic science, discussed previously in connection with contemporary infrasound research building upon the foundational 19th century Krakatoa observational data, represents one particularly clear and particularly well-documented example of how this specific historical eruption has continued to inform and to motivate subsequent scientific disciplinary development, with contemporary infrasound researchers continuing to cite and to reference the historical Krakatoa data as foundational evidence within the broader scientific literature addressing this specific and scientifically significant category of atmospheric acoustic phenomena. This broader pattern of continuing scientific legacy and continuing scientific influence, extending from the original 1883 eruption through more than a century of subsequent volcanological, acoustic, and atmospheric scientific research and subsequent scientific disciplinary development, illustrates how major historical natural disasters, when sufficiently well documented through contemporary scientific investigation and subsequently maintained within accessible scientific archives and accessible scientific literature, can continue to generate genuinely valuable and genuinely ongoing scientific research value extending very considerably beyond the immediate historical period of the disaster event itself, connecting this historical 19th century volcanic catastrophe to ongoing and genuinely active contemporary scientific research addressing volcanology, acoustic science, and atmospheric science as recognized and continuously developing academic and scientific disciplines. The central image that emerges from this full historical and scientific reconstruction of the Krakatoa eruption is one of an explosion of such extraordinary physical violence and such extraordinary acoustic and atmospheric reach that its consequences were simultaneously experienced, in radically different forms, by populations across virtually the entire inhabited world. From the immediate and catastrophic mortal danger faced by coastal communities in the Sunda Strait to the considerably more distant and considerably more aesthetically curious experience of observers in Europe and North America documenting unusually vivid sunset coloration, to the genuinely puzzling experience of listeners on a remote Indian Ocean island who heard a sound whose true source they could not possibly have imagined. The eruption's specific combination of catastrophic local destruction, remarkable and scientifically unprecedented long-distance acoustic propagation, and genuinely global atmospheric and optical consequences, all occurring within a historical period when the relatively newly established international telegraph communication network had just become sufficiently developed to transmit news of this catastrophic event to populations across the globe within a remarkably compressed and remarkably modern-feeling time frame, makes Krakatoa a particularly significant historical case study for understanding both the genuine and extraordinary physical power that volcanic eruptions can unleash and the broader historical development of how human societies have experienced, processed, and communicated about major distant catastrophic events occurring at considerable geographic remove from any individual observer's own immediate community. The specific continuing scientific legacy that this eruption has left for subsequent generations of volcanologists, acoustic scientists, and atmospheric scientists, extending from the Royal Society's pioneering 19th-century scientific investigation through more than a century of subsequent scientific research and subsequent scientific disciplinary development, illustrates how this specific historical catastrophe has continued to generate genuinely valuable scientific insight and genuinely valuable scientific case study material extending very considerably beyond its own immediate 19th century historical period, connecting this historical eruption directly to contemporary scientific research addressing volcanic hazard assessment, tsunami early warning system development, and the broader physics of atmospheric acoustic and atmospheric optical phenomena. The continuing volcanic activity at Anak Krakatoa, including the catastrophic 2018 collapse and associated tsunami that this documentary has discussed, serves as a sobering and historically resonant reminder that the specific geological forces that produced the catastrophic 1883 eruption continue to operate within this same geographic region in the contemporary present, connecting this historical catastrophe directly to ongoing and genuinely consequential contemporary natural disaster risk management concerns facing the considerable contemporary population that continues to inhabit the historically hazardous coastal regions surrounding this demonstrably active and demonstrably dangerous volcanic site. A continuing connection between historical catastrophe and contemporary risk that this documentary has sought to examine and to communicate throughout its broader historical and scientific reconstruction of this remarkable and genuinely significant natural disaster. The physical locations and specific museum and archival collections where contemporary visitors and researchers can encounter direct evidence and direct historical documentation connected to the Krakatoa eruption provide meaningful opportunities for tangible engagement with this remarkable and historically significant volcanic catastrophe. The remnant of the original Krakatoa volcanic structure, along with the considerably more recently emerged Anak Krakatoa volcanic island, remain accessible to scientific researchers and, under appropriately careful and appropriately monitored circumstances given the site's continuing active volcanic status, to limited numbers of tourist visitors, providing direct physical access to the dramatic and continuing geological legacy of this catastrophic eruption, including direct observation of the considerable caldera structure that the original 1883 eruption's catastrophic explosive collapse created. The Royal Society's original comprehensive scientific report addressing the Krakatoa eruption's documented global consequences, discussed previously in connection with this pioneering 19th century international scientific investigation, remains accessible to contemporary researchers through various academic library and academic archive collections, providing direct access to this historically significant foundational scientific document and to the considerable body of original 19th century observational data and original 19th century scientific analysis that this comprehensive scientific investigation compiled and published. Museums and archival collections across Indonesia, the Netherlands, and numerous other countries maintain various historical artifacts, historical photographs, and historical documentary materials connected to the eruption, including, in several cases, preserved colonial administrative records documenting the eruption's catastrophic local mortality and local destruction, providing researchers and interested members of the public with direct access to primary historical source material, documenting this catastrophic event's immediate human and material consequences. This combination of direct physical access to the continuing volcanic site itself, alongside access to the considerable body of preserved historical scientific documentation and preserved historical administrative records connected to this remarkable eruption, provides genuinely meaningful and genuinely substantial opportunities for direct historical and scientific engagement with this catastrophic and historically significant volcanic disaster, connecting contemporary researchers and contemporary interested members of the public to both the dramatic continuing physical legacy of this eruption and the considerable body of careful contemporary 19th century scientific documentation that this catastrophic event generated. The ongoing scientific research connected to the Krakatoa eruption and to the continuing volcanic activity at the surrounding Anak Krakatoa site continues to develop along multiple active contemporary research directions, as volcanologists, acoustic scientists, and natural disaster risk management researchers continue to apply new scientific techniques and new categories of available evidence to deepen contemporary understanding of this historical catastrophe and its continuing contemporary geological and scientific significance. Continued volcanological monitoring and continued volcanological research addressing Anak Krakatoa's ongoing volcanic activity continues to refine scientific understanding of the specific underlying geological processes governing this developing volcanic structure's continuing eruptive activity. Work that has gained considerable additional scientific urgency and considerable additional scientific attention following the catastrophic 2018 collapse and associated tsunami, as researchers work to develop increasingly sophisticated scientific understanding specifically intended to improve future volcanic hazard assessment and future volcanic hazard early warning capability for this demonstrably active and demonstrably dangerous volcanic site. Continued acoustic and atmospheric scientific research, building upon the foundational 19th century historical Krakatoa data discussed throughout this documentary, continues to refine contemporary scientific understanding of infrasound propagation physics and atmospheric volcanic aerosol behavior. Work that connects this historical eruption's scientific legacy to ongoing contemporary research addressing both natural volcanic infrasound sources and the broader category of atmospheric infrasound phenomena more generally, including infrasound generated by other natural and artificial sources that contemporary infrasound monitoring networks continue to study and to document. Continued historical and demographic research addressing the eruption's precise mortality toll and precise broader social and economic consequences continues to develop increasingly refined and increasingly methodologically careful historical understanding of this catastrophic event's full human and societal impact, building upon the kind of careful historical demographic reassessment methodology that this documentary has discussed in connection with several other major historical catastrophes, contributing to an increasingly complete and increasingly nuanced historical understanding of this remarkable eruption's full historical significance. This continuing and genuinely active multidisciplinary scientific and historical research engagement with the Krakatoa eruption, more than a century after the catastrophic 1883 event itself occurred, illustrates how this historically significant volcanic catastrophe continues to generate genuinely productive and genuinely evolving scientific and historical research across multiple academic disciplines, with each new methodological advance and each new category of available evidence continuing to deepen and to refine contemporary understanding of exactly what happened during this remarkable eruption and exactly how its consequences, both historical and continuing, have shaped subsequent scientific understanding and subsequent natural disaster risk management policy across the more than 140 years that have elapsed since this catastrophic eruption's original occurrence. Tonight, in the Sunda Strait between Java and Sumatra, the volcanic island of Anak Krakatoa, the child of Krakatoa, continues its ongoing pattern of periodic volcanic activity, a continuing and direct geological descendant of the catastrophic 1883 eruption that produced the loudest sound ever documented through scientific instrumentation in recorded human history. The sound of that eruption, traveling outward from the Sunda Strait at the speed of sound through the atmosphere, reached listeners on a remote Indian Ocean island nearly 3,000 miles away, listeners who heard what they reasonably but incorrectly interpreted as distant naval gunfire. having no possible way of understanding that they were hearing the direct acoustic signature of one of the most violent explosive events in recorded human history, a sound whose true source would only become clear to them once news of the catastrophic eruption traveled back to them through the relatively nascent international telegraph communication network that, by historical coincidence, had only recently become sufficiently developed to carry exactly this kind of urgent and consequential news across the considerable geographic distances separating the world's populated regions from each other. What remains, more than a century later, is a body of historical and scientific evidence that the Royal Society's pioneering 19th-century international scientific investigation began to assemble within months of the eruption itself. Barometric pressure records documenting the eruption's atmospheric pressure waves circling the entire planet multiple times. Observational reports of unusually vivid sunset coloration submitted by observers across Europe and North America, and careful documentary records attempting to establish the eruption's catastrophic human toll among the coastal populations of Java and Sumatra, who experienced this volcanic catastrophe's most immediate and most devastating consequences. The specific combination of catastrophic immediate local destruction, remarkable and scientifically unprecedented acoustic propagation, and genuinely global atmospheric consequences that this single volcanic eruption produced, all occurring at precisely the historical moment when international telegraph communication infrastructure had just become sufficiently developed to transmit news of this catastrophic event to populations across the globe within days rather than weeks or months, makes Krakatoa a genuinely unique and genuinely significant historical case study connecting the raw physical power of volcanic eruption to the broader historical development of global communication, global scientific collaboration, and global historical memory, a combination of historical significance that continues to make this remarkable 1883 catastrophe a subject of genuine and ongoing scientific and historical fascination more than a century after its original, catastrophic, and unforgettably loud occurrence. If this documentary kept you company through the night, there is more waiting for you. Choose the next film on screen, and let the story keep unfolding.